Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our calculus series here. We just recently finished doing an example on absolute maximum and minimum. So let's continue with another example just to build up on that stability. Uh, okay, so let's just hop right into it. Okay, so for the next task, we want to find the absolute maximum and minimum values of f on set D. So let's quickly do that. So we want to find absolute max and min of a function. So we'll specify that's function f on some set we'll call D, right? So here's our specified function. It's a function of two variables, x squared plus 5y squared minus 2x minus 10y. Is that right? Yeah, then plus 1. And this is bounded by some set D where each xy point has a rule or has a set of restrictions. The set of restrictions are in the x coordinate, it's bounded by 0 and 2. In the y coordinate, it should be points or y coordinates in between 0 and 3, including 0 and 3. Okay, so how do we go about such a problem again? First, we find critical point slash points. That's the first step. And so we get their partials. So this is 2x, 0, minus 2, 0, 0. So 2x minus 2. F, oh, we set them to 0 as well. I almost forgot. Here we do the same thing. 10y, 0, minus 10. We set it to 0 as well. And then from there, now we want to, oh, we can solve for each of these. So we get 2x minus 1 is 0. Divide that, x is 1, right? Here we divide it by 10. Or we factor out the 10. That's what I mean. And then we see y is 1. And so our critical point, so this is one of our, I guess, lucky cases because we don't have to solve some system of like we have two variables in the same equation. Because if that was the case, then we need or we have a system that we need to solve for both the two variables. In this case, we don't. And so after we solve this critical point, let's immediately get its output or its value. So here we plug in the ones, 1, 1, 1, 1. We get 1 plus 5 minus 2 minus 10 plus 1. Don't know why I talk like that. 6 minus 2 minus 10 plus 1, -5. This looks like a minimum, but we'll find out sooner or later. Okay, let me go ahead and find what's the next step? Extreme values. What do I mean by extreme values? Here we look at endpoints, we look at maximums, we look at minimums at each of these critical values. Right? So let's look at the domains here. Here we see a couple of cases. Let's start with the X cases, right? So what are the X cases? Well, we can say Okay, this is 0 and 2 because those are the endpoints. What else can we say? We already have a critical point, x is 1, y is 1, so we're good on that. So it's just x is 0 and x is 2. So here, I think that's one of the difficult things, or one of the difficult things, is identifying which are the cases. I think it was 2, right? Oh shoot, I wrote 3. So an x is in between 0 and 2. What is that? Is that critical value? Is that it is an endpoint, but from there we have to identify these minimum, we have to identify these values, right? So let me go ahead and do this. So when my x is 0, that's fixed. And I have my y here. What would be that? What's the output of that? Well, let's solve it. We have 5y squared minus 10y plus 1. Done, right? I just made all of the x's 0, so they're gone pretty much. Gone, gone. I'm left with these 3 terms in the right-hand side. And then I'm going to do the same thing here. So here, instead of 0, I'm going to put 2. So this one's a bit more iffy. So this one's 4. Safe. Minus 4. Oh, that's 0. Cool. 10y or minus 10y plus. Oh, I get the same thing. That's funny. So I actually get the same thing here. Now, this is an upward parabola. Or I shouldn't say upward. It's a concave up parabola. And so if we take the derivative of this, we set that to 0, we get its minimum. Right? So let's do that. We take its derivative, we get 10y minus 10. Y is 1. Wow. We plug that in. F of 0, 1. And we get, I don't know, what do we get? We get f of 0, 1. 0, 0, 1, 6. We got 6. Wait, I'm looking at the wrong one. I'm looking at number 7. Okay, so I get, that's funny. I got 0, 1, 0, 1. Okay, I got 5. What's this? Minus 10 plus 1. 6 minus 10 is negative 4. There we have it. We have negative 4. How do we get the maximum value? Well, what's the end of our domain for y? Oh, it's 3. Okay, let's go ahead and use that. So when, okay. Actually, another thing we could have done. Oh no, actually this is fine because it's a quadratic, right? So it's better to use this. So to get the maximum this time, we just use the endpoint of our domain. So here we get, or honestly, we could try all of them. It doesn't even matter. We just try all of them. We try the endpoints, and then we try the when we take the derivative. So let's just do it. If we make these 0, we actually just get 6, right? Or no, we get 1. Yeah, we get 1. So actually, funny enough, I think that's the minimum. I'm kidding. That's not the minimum. See how sometimes this bigger y can be a lesser number. So this one's definitely smaller than negative 4 is definitely less than 1. So here we can see that this is a more minimum value compared to this. And then we can try the other the other endpoint when y is 3. So let's go ahead and do that. So when y is 3, right? So I'm just including both endpoints. Uh, Let me see. 0, 0, gone. I make this 3. I get 5 times 9, that's 45. Minus 30. Plus 1. What is that? That's definitely a bigger number, if I'm gonna be honest. Okay, I get 16. Yeah, that is a bigger number. So here I get that output, I get 16. And here we can see this is definitely indeed a maximum, right? And let's do the same thing. Here we have f of 0, 1. Let's not go through the same process again. Oh, my bad. Actually, let me go through the same process. I take the derivative, I get y equals 1. But here, instead of 0, I actually get 2, 1. Right? So when I'm replacing 2 instead of 0, I think I should still get the same thing, right? Let me see. 2 and 1. This one gives me a 4. This one gives me 1, 5 minus. This one gives me 4. Then 1. Cancel, cancel. 6 minus 10. Oh, it actually gives me the same thing. That's funny. So this is the same thing. Any reason? I don't know. I'm not sure yet. But if you guys do know, is if there's like some sort of pattern just to make my solving quicker, we should definitely get on that. Okay. Now we look at my minimum and maximum. Or my endpoints, I mean. So we look at f of 2, 0. We also look at f of 2, 3. Same idea, right? So when I do that, 2, 0, 4, 4 plus nothing, minus 4, that's nothing, minus, oh, that's nothing. Okay, I got 1. So 2, 0, I got 1. Oh, so look at that. It's kind of the same thing. Negative 4, negative 4. 1, 1. Let's see if this is also 16. 2 and 3. 2, 3, 4, 9, 45. Minus 4, that's 0. Minus 10. Oh, I actually do get the same thing. Because this is minus 30 plus 1. So I get 6 negative, no, not negative 16. I get 16. I still do get the same thing. So there is some sort of pattern here. Yeah. Okay. And then from there, so those are our extreme values, the endpoints, the minimum, the maximum. Okay. Now let's look at when y is 0 and when y is 3. When y is 0, we actually get a function where, like this, we're trying to find x when y is a fixed constant, which is 0. So when y is 0, x is nothing. So this is 0, 0, gone. We have x squared minus 2x plus 1. And funny enough, that is a perfect square. X squared minus 2x plus 1, that's just x minus 1 squared. Let me just double check, just to see if I'm not messing anything. Okay, I'm not messing anything. So that's that. And then from there, we get the derivative. So we set the 0, get the derivative, do a chain rule, 1. So that's gone. X is 1. Right? Now we plug it in. F of 1. What else do we have for our x values? We have 0. We have 2. So we're going to do it when x is 1, when x is 0, when x is 2. Now, just to make our lives easier, did we already solve this before? We solved for 2, 0. 2, 0 is 1. 0, 0, 1. Now we haven't solved this, right? No, I don't think we have. No, we didn't. So 1, 0, let's quickly do that. 1, 0, 1, 0, 0, gone, gone, 1, 1 minus 2 plus 1, 0. Okay, let me just erase my erasures. So this is 0. Now here, we do the same thing when the case when y is 3. Instead of 0 for y, we make it 3. We get, I don't know. So we always plug it back in here. 3 was this x squared, 3, that's 9, 45, 31. X squared minus 2x, 45 minus 30, 15, 16. X squared minus 2x plus 16, right? So I'm kind of seeing the patterns here. So this is, again, x squared minus 2x plus 16. Is there a perfect square? I don't think I need to find one. But in the case 4, there isn't. I can't factor out anything here. So I would use a quad formula to solve this. Yeah. Okay. So I would just take the derivative. 2x minus 2. Done. What's this? 2 times x minus 1. X is 1, right? And so we do it again. F of when x is 1, 1, 3. When, okay, what else? Y is 3, y is 0. And what was the other one? Y is 0, y is 3. I think I'm messing up something. When x is 1, yeah, because these should have the same things. Oh, now I see why I'm messing up. These are all going to be 3s. So the thing I'm messing up on is the endpoints. So I have to find the endpoints of x, so that's 0 and 2. Yeah, so this is 0, this is 2. Is there something similar here? Well, we can see 0 and 3. That's 16. Here, looking at this one. What else? Do 3. Oh, do 3 is also 16. You know, I wouldn't be surprised if 1, 3 is just 0. But I think it is. Let me see. So 1 and 3. Because I think I'm recognizing a pattern here. But this is just in particular for rectangles, right? So this is 1, 45, minus 2. Just add minus 30 plus 1. And let me add all of them. Is that 0? 1 plus 45 minus 2 minus 30 plus 1. Oh, so it isn't. Okay. Right? Let me see. Yeah, it's 15. 1 plus 45 minus 2 minus 30 plus 1. Yeah, it's actually 15. My bad. I thought I got a pattern there. I was thinking, wait, maybe it's the same for here, but I guess not. Yeah, because this one's different. 16 instead of 1. So this has to be something else. Is there some pattern? No, there isn't. It's only for the X part. This one is different. Interesting. Okay. So probably some general formula we can come up with just for this problem to make it super quick. I'm gonna leave that to the nerdy nerds. They could make a formula to make this quicker. But I'm not gonna do it here. And I don't plan on doing it. I'm not that hardworking. Okay, so from there, oh my God. Now we find which one's the absolute max and min. Which one's the biggest number? 16, right? this is an absolute max. Right? Absolute max is 16, and they're located at 2, 3, 0, 3. Yeah, 0, 3, and 2, 3. And then the minimum is actually the critical point. This is the minimum, the absolute minimum. And it's only at -5. Okay, that's cool. Let's do another one. Wait, did we get that? Oh, nice, we did get it. Okay, we're just trying to do more of these just to get the hang of it. So again, we're trying to find the absolute max and min of some function f restricted by a set D. So let me see. Here we have a function, f of xy. This is equal to 2x cubed plus y to the fourth plus 2. Then my set D is the rule that if we're given an xy value, hey, look at that. My x squared plus y squared is less than or equal to 1. So I'm talking about a unit circle here. And if it's less than or equal to, I'm talking about all of the points in the circle as well as on the circle. So on the circle, in the circle. That's what I'm talking about. Okay. So again, how do we do this? Well, same steps. Find critical points. Slash s, because I could have a multiple. We take their partials. With respect to x, I get 6x. That's it. 6x squared. With respect to y, I get 4y cubed. Oh, that's, yeah. And then from there, we solve for x and y. So here we have x squared is 0. And so that just gives us x is 0. Y cubed is 0. That gives us y is 0. So our critical point is the origin. 0, 0. Let's get the output immediately. F of 0, 0 is 2. Oops. Okay. Now let's find the absolute max and min. So max and min, or no, I mean extreme values, my bad. Find extreme values. So this is what? Let's look at cases. What can we see? Well, if we're looking at it, what can we see from this domain? What are my cases for x and y? So this is the first time I've encountered, again, something like this. I don't know what x squared is. I don't know what y squared is. I don't know how to solve for each of them. So what I would do again is I would Google, because I don't know, obviously. I do have the answers though, so I know if I'm getting it right or wrong. See, but that's the idea of math. Like when I, at least for me, when I encounter something new, I try to think about it for a bit. I don't get it, I Google. Okay, so I get their partials. Did I get the partials correct? Okay, I got correct, the partials. I set them to 0, and I get the critical point, which is the origin. And then I plug it in. I get f of 0, 0. I get 2. That's good. Now I analyze the function on the boundary of D. Now, what is that? So I think that's an extra step we can find in case we don't know. Okay. So the way we can, so I'm gonna add an extra step. It's like a little detour. But how do we find cases? That's our main goal. We want to find the cases when x is 1, when x is 0, when x is infinite. Okay, not infinity. When y is 1, when y is 12, stuff like that. By here, we're going to analyze the boundary, right? So the boundary is that x squared plus y squared is less than or equal to 1. Now, to analyze this, let's maybe look at the case where it's equal first, right? So if we look at the case where it's equal, then what do we see? We can say, okay, y squared is equal to 1 minus x squared. You could do that. We could substitute that to xy, f of xy here. So okay. So instead of it being 2x cubed plus y to the fourth plus 2, I would substitute the y squared here. So this is actually the same as y squared squared. So what I would do here is just put this whole thing and square it. So I get this, and now I have a function of one variable where my y is in terms of x. So now I'm going to say this is equal to some function g, right? Let me simplify it. I'm going to simplify this thing. So I got 2x cubed plus, and I think this was, let me expand. So I got 1 minus x squared minus x squared minus 2x squared. Did I get that right? Yeah, minus 2x squared plus x to the fourth, right? So I'm going to say plus 1 minus 2x squared plus x to the fourth plus 2. And then I could simplify this even further by adding the two things, the two numbers. So I get something like, then I'm also going to format it, x to the fourth plus 2x cubed minus 2x squared plus 3. Now I get something like that. And then what? Now I can find the critical points of this thing, right? Okay, let me put some steps actually. So we analyze the boundary. What did we do here? So here when I'm encountering something new, I would just do this. Substitute y in terms of x. What would be the reason for substituting? Play around. That's one thing. Make my life easier. It's another thing. I don't know. We'll see. We'll see what happens. And then from here, now I find my critical values or critical points. So I do that same thing again where I take, now here in this case, I take the derivative because I don't know, this is a one variable. So I don't take partials. So I get 4x cubed plus 6x squared minus 4x, right? Then I make that equal to 0. Let me actually simplify it a bit. I can factor out the 2x here. So I get something like 2x, that's 4. So I'll put 2 here. And this is 3x. And then this is minus 2. And then that's equal to 0. Right? So I'm just trying to simplify everything. And then from there, I see two things. My 2x being 0, as well as my other term being 0. Now, what's the hard part? How do I find this one? That's algebra. So x is 0 here. Now here, what's x? Or actually, I could just go ahead and use a quad formula. It doesn't matter. To make my life easier, I'm just going to use a quad formula. So I get negative b plus minus square root of b squared minus 4ac over 2a. Here I get negative 3 plus minus, this is 9, minus, and then another minus, so that's positive, plus 16 over 4. And then from there I get something. 25. I actually get 5 here, believe it or not. I get 5 here. Oh, I got two things. So for my x values, I actually get negative 3 minus 5 over 4. So I either get a negative 2, or when I add it, so 5 minus 3 is 2 over 4, I get 1/2. Now, which one is it? That could be both. I don't know. Let me see. Oh, I'm kidding. What? Oh, yeah. Negative 2. Oh, so what do we realize? The critical points are within negative 1 and 1 for my x, because I'm looking at a unit circle. This unit circle tells me my x is in between negative 1 and 1. So that's what it means to analyze the boundary. This is negative 1, this is 1. Radius of 1, this is 1, this is negative 1. My y and x plane, right? And so if I get something beyond the scope of my domain, I immediately disregard it. So I actually just disregard the negative 2 here, right? Because this is not in domain. This one's in domain, so I'm going to keep this. This one's also in domain, so I'm going to keep this. So yes, I have x equals 0 and x equals 1/2. So now I have these two x cases. That's how I got these two x cases. And then I evaluate, oh, to make it easier actually for me, I could evaluate everything here and then get something. I'll get a y value out of it. That's what's fascinating. So I could just use my g of x to do this, right? At g of 0, at g of 1/2, and then at g of 1, and then at g of negative 1, right? That's interesting. Then I get some values out of it, and then I compare, right? So here I don't even need to log my y values. That's for a different case. That's for rectangles. This one's for circles, right? So let me just do that. Now to find the now I log my cases. So my cases are when x is 0, when x is 1/2, and then the endpoints when x is 1 and negative 1, right? How do I know? Actually, I don't. Now I plug in g of 0 is some value, 3. G of 1/2 is some value. I'm not even gonna bother. 45 over 6, apparently. Over 16. G of 1 is 4. G of 0 is, I'm assuming just a 0. Or no, G of -1, my bad. G of -1 is 0. So what I did here was I plugged all of it here. All the x values here. And then got some output, G of x. And then after that, now I compare all of these values and I find that, okay, what's the absolute minimum or absolute maximum? So the smallest number bit from 2, 3, 45 over 64, 0. Well, it's just the smallest value is 4. What? What's the smallest value for? Oh, the smallest value is 0. I bet. I was looking at something else. So the smallest value is 0. This is the absolute minimum. Absolute min. My biggest value, however, is 4. What is this actually? 45 over 16. Is that greater? Oh, it's like 2 point. Oh, no, it's an exact value. 2.8125. So this one's the bigger value. This is the absolute max. Right? And then from there, I'm good to go. That's it. That's all the problem's asking. Cool, cool. Okay. Let me see. Another one. Hmm. Find. Okay. Let me see this. I have like a couple more. Okay, let me do 2 of these. So the next one's a bit interesting. It's not about, or I think it is about finding these maximum and I don't know. Here we want to find points on the cone. So it's a cone, it's a quadric surface with this equation. Z squared is x squared plus y squared. And its closest. See, that's a hard thing to define in math. What do we mean by close? Is it on the quadric surface? Right? Because a cone looks something like what? Like that? Let me see, actually. What is this specifically? If I take out my z, I get some number. That's a circle, right? So that's a circle in the xy plane. If I take out my x, what's that? This is some k. Z squared minus y squared is equal to k. That's a hyperbola, right? Because it's a minus at the x, or no, not x, yz plane. And it's the same thing. It's a hyperbola as well in the xz plane. So it's a hyperbolic circular hyperboloid, but I guess it's just a cone. Let me see what that looks like. Circular hyperboloid. I would, yeah, hyperboloid, and it is a cone. Yeah, it's a cone. Cone in 3D. Yeah, it's a cone. I don't know why they call it that way. That's just dumb, if I'm being honest. Okay, so let me just go through this and see how like people would solve it closest. Okay, so first thing, so here we're doing closest, right? So here we're most likely doing a shortest distance formula again. And we have steps for that, right? So we find the distance from the point to the plane, here from the point to a general quadric surface, say a cone. Then we replace z, we find the critical points, we plug into the distance formula, those critical points. As simple as that. Okay? So I quickly do that. So find distance from xyz all the way to this point, 8 to 0. Here we just use a distance formula. As simple as that. So I do x minus 8 squared, y minus 2 squared, z minus 0 squared. I'm just gonna complete the whole thing. Let me see if that's what it's trying to do. I don't want to like get ahead and then I see that, oh my god, I'm wrong. Okay, so again, same idea. I replace, what's this? Oops, my video's still playing. Yeah, so I replace z with something here. So here I replace z in terms of x and y, right? That's what I want to do next. So again, same steps. So replace z in terms of x and y. So here, let's look at our original quadric surface equation. We have this. Actually, we kind of don't need to because this is already z squared, and we actually have it here already. So let's immediately square the thing. And that will be our f of xy. So this is x minus 8 squared, y minus 2 squared, plus x squared plus y squared. Right? Now we have that. Okay, let me see what's next. Can I get this? Okay, now again, I find critical values, critical points, right? That's the next step. So I take partials in terms of x and y, plug them, make them 0, solve for critical points, plug it back in. I didn't know it was that simple. So I solve for critical points. Where in the world am I? So find critical points. Easy. F sub x. What is this? I take my partial, chain rule, I get 1. That's 0. That's nothing. X squared, that's 2x. Y squared, that's nothing. Can I simplify maybe? 2x minus 16 plus 2x. Oh, I get 4x minus 16. And then I get 4x times 4. Or x minus 4, my bad. Then I just equate that to 0. And here I see x is 4. Right? Then I do the same thing here. F of y. So what actually makes this easy is that I don't have to solve a system. Because I don't have a term where I have both x and y on that same term. This is a separate term, separate term, separate term, separate term. I only have one variable in each term. So when I take the derivative, I'm good. Because I got to erase the other one. So here I make that 0. This is 2, y minus 2. Chain rule that, we get still that. And then this is 2y. And so let me just, this is 2y minus 4 plus 2y. We get 4y minus 4. We get 4y minus 1 equals 0. And so here we get y is equal to 1. And that's our critical points. Then from there, we just plug those in. I think that's the next step, right? Hopefully. Unless I do something else. So I plug it back in. Let me see actually if that's the same thing, because I feel like it might be different. Let me just quickly go ahead and do that. So I make them 0, get the critical points, and then oh, I just plug it in. Oh crap. Okay, so I plug it in. Oh, that's cool. Okay, so plug in. I think it was a distance, right? Oh no. So here's the difference. It's not asking for a distance. It's asking for points on that cone. And so I just want to plug in X and Y to that cone, right? So plug into, or not cone, let's make it general, to surface equation. Because I want to find points on that cone closest. So I just do z squared equals x squared plus y squared. This is just the same as z squared equals, I plug in my 4, I plug in my 1. Where's that? Wait a minute. Oh yeah. And then from there, because I need an ordered triple, right? Now I need to find my z values. This is going to give me 16 plus 1, 17. This is 17. And so my z is actually two things, plus minus square root 17. So my points that are closest would be 4, 1, square root 17, and 4, 1, minus square root 17. Those are my 2 points. And I think that's it. Yeah. So it's actually easy when we get the steps down, right? Just take note of the pattern and we're good. Okay, let's do like, okay, we have like 4 more problems. Let's do all of them. So again, same idea. Let me do one more. So here we're being asked to find points on this particular surface. So here now we're making it general. So y squared equals 64 plus xz closest to origin, right? So here we need to do a distance formula. So find distance from xyz to, yeah. Really, the idea about doing math in uni is finding the pattern and then doing it. We're not really memorizing the pattern, but quote unquote understanding. And this was, I believe, origin, so 0, 0, 0. Oh, that's actually just the distance from these things, right? Then from there we plug in, or we find, we replace, or actually, let me check. Is this on the surface? 0, 0, 0, so it's not, right? So we replace z in terms of x and y. How would that look like? So I have this thing. Now I want to isolate my z here. So I got y squared minus 64 is equal to xz. My z is just then y squared minus 64 over x, right? And then from there, I'll plug it in. So I got d squared is that function of f of xy. This is x squared, y squared, z squared. So I think this was y squared minus 64 over x squared. Okay, can we make this simpler? This term at least. I want to see if we can make it simpler. Hmm. I don't think I can get. Yeah, I'm okay with this because I know if I try to make it look like I'm gonna get the product rule, I'm eventually gonna do a quotient rule, so it doesn't matter. Anyway, so here we again find critical points. And that's gonna be okay. F sub x. So I just take note of what I have here. I got what in the world is this? 2x, y squared is 0. This one I put the 2 here of whatever's inside times whatever's inside. And I do a chain rule of this thing. So I do, okay. So I do my quotient rule, low derivative of high minus high below over low squared. So x squared. Oops. So which one do I remove, right? Well, I'm doing x, so this one's 0. That's gone. This one is gone. That's 1. This one is minus y squared plus 64. So I'm going to say, okay, this is 64 minus y squared. I'm just going to leave it like that. And there we have it. So that's 64 minus y squared over x squared. So 64 minus y squared over x squared. Right? Cool. And then from there, we're done. Now we equate them to 0 basically. I can factor out my 2. This is not clean. Not clean at all. Okay, let me see. So let me factor out my 2. So I'm going to say that's x plus this thing times this thing. No other way, huh? Trying to make it look clean. But I guess I can't really. Okay, cool. I could take out my 2 now. Just trying to clean it up. So I divide both sides by 2. And then now what? Mm, this term was a mess. I don't expand it. Or do I? Mhm. Wait a minute. How do I find critical points from here? Because now this is some sort of like system, right? Oh, never mind. Because now I have x and y, so now I need to find something else. So I do f sub y. So now I have y squared. And I think I know the pattern. Y squared, then I just add it to chain rule of this, right? So I kind of do the same thing. But then here, I just make it, oh, okay. Let me just do x above and y at the bottom. I think that's it. Or I might be wrong. Just to make sure, let me go ahead and do the chain rule again. So I'm going to say my low derivative of my high minus high derivative of my low over low squared. So after I still get the x squared here, I just get a 0. because my x prime is 0. Here, I get 2y. So I got 2xy over x squared. And I can factor this out. So I get 2y over x. Right? I could factor out the 2, make this a 4. I could do that. Do I want to do that? Whoa, this is a complicated term. What the freak? Okay. Uh, that's not nice. Could make this 4. Oh, okay, fine. I'll have to. So this is y over x. I'm gonna clean it up here, right now. Factor out the 4, that's good. Here I get I think here I get y cubed minus 64y over x squared. So I could just say that. Just to make it as concise as we can. So this is y cubed. This is 64y. This is x squared. And then from there, okay, let me... Can't really do anything here because this is just... Okay, this is 0 again. And this one was way, way cleaner. So I could just immediately get the critical points. Here, I have to work my way to get the x and y values. It is possible, but it's just hard because of all of the things happening here. Is there a way to make it cleaner, maybe? I don't want to factor out anything that's weird. This is okay. That's not good. I could replace this and then put all. That's weird though. That's really weird. No way. Okay, I give up. I don't know how to make it like super clean, but that is really weird. Super weird. Oh shoot, I just realized. If I have a y squared, does that mean I replace instead of z, I should have replaced y? Should I have just done that? Is that like the idea behind it? Okay, why are we using Lagrange multiplier? There's no way we do that. And of course they did that. That's nice. What if I try doing that instead? I don't know, just to see how it works. Because I do have it here. So why make it harder, you know? Let me actually try that instead of doing that. What's the easiest thing, right? So here I realize, okay, maybe it's not that easy to find. It's getting more convoluted every time I look at it. So I think that's not, no way they would have put that in the homework. So I'm gonna say that's not it. Okay. What instead I'm gonna do is I'm gonna keep this y squared thing and then just replace y in terms of z and x because I already have that. So I'm going to replace y in terms of z and x. So here I say, okay, well, let me go ahead and square this thing, which will just be my function of x and z instead of x and y. And then from there, okay, let me, what am I doing here? Oh, I got x squared plus my y squared is what? 64 plus xz. plus z squared. Right? This looks way more cleaner, in my opinion. And then from there, now we find critical points of this function. And so we get their partials in terms of x, one's in terms of z. We set it to 0. So in terms of x, I get 2x plus 64 plus z. Done. Or no, 2x plus z. That's it. This is equal to 0. Here we get f of y. This is, or f sub, not f sub y, f sub z. See, now I'm used to y. Now here I treat z as a variable. So here I have 0, 0, x plus 2z. Oh, look at that. 2z plus x. Oh, that nice pattern. Here I can change z to be negative 2x. And so here I get 2 times negative 2x plus x equals 0. I get minus 4x plus x. I get minus 3x. So x is 0. And so z is 0. Boom. Got my 2 points. And then from there, I plug it in, right? So after I find my critical points, I just plug it in to get my y value. So I do f of 0, 0. I get 64 though. Oh no, I plug it in my distance formula. Is that it? Wait a minute. Find points on the surface closest to the... Oh, it's on the surface. So I have to plug it in my surface equation again. Yeah, so I plug it in my surface equation. So plug in surface equation. So here I do y squared is equal to 64 plus xz. So that's going to be, oops, xz. Here in this case, it's actually just 64. And so my y is just, well, plus minus 8. And so my 2 points from that surface closest to the origin are 0, 8, 0 and 0, negative 8, 0. Okay, I'm going to stop the video there because I know it's going to be too long. I'm still going to go through some exercises here, but I hope you guys enjoyed. And yeah, I'll definitely all see you in the next one.